Okay, the last part of this set of notes in section 5.8 is more in there because there are certain algebra techniques that you need to kind of be more skilled with as you are working with integrals. So for example, in taking a look at this problem, you initially may believe that this is a u substitution where you're going to let u equal your 4 minus x squared because you have this x up here in the top. What our problem is that du is going to be negative 2x dx, and what we're missing in this derivative is that you're missing the plus 2 part, and that's not really something you can fix. And so what you have to recognize in this problem is that sometimes you need to split them up. Like sometimes the algebra that you are going to need to do in order to do this integration is to split this, because the sum with a fraction can be split as x over square root of 4 minus x squared dx plus the integral of 2 over square root of 4 minus x squared dx. And that when you split, because the integral of a sum is the sum of the integrals, then we can do our problem. And what we'll see is that this one right here is going to be a power rule. And this one here is going to be an inverse trig rule. And it's going to be your inverse arc sine when we look at that. And so it gives us a way of looking at it where we have to do some extra work. And so here with the power rule, I am going to do this substitution, which I already wrote down, so I'll bring it over here. We are missing a 2, actually a negative 2, so I'm going to add that in, and I'm going to add a corrector. And so for this portion, we're going to have negative 1/2 antiderivative of 4 minus x squared to the negative 1/2 because it's power rule. And then we have the negative 2x dx there. For the moment, just put a plus. We'll come back to that. This is going to become negative 1/2 the integral of u to the negative 1/2 du. And so that's what we're going to be integrating for this side. All right, now if we look at the other one over here, we would like to say, well, this one is an inverse trig. So when we're doing this problem, we use the inverse trig strategy. The 2 is going to come out, and because that doesn't bother me, that's a constant, so 2 antiderivative of, and because I have dx over square root of 4 minus x squared dx, I'm going to let a equal 2. I'm going to let u equal x, and my du equals dx. So on this one coming down, we would have 2, and we would just go straight to our arc tangent. We don't have to make any substitutions, or we can. Du, I just realized I have too many dx's there. I moved it up to the top. So we have our du is dx. The bottom is going to be the square root of 2 squared minus u squared, changing everything to u. And so now we're ready to do our integration for both of these problems separately. Now, sometimes when you are doing problems and I'm doing a different u over here than I'm doing here, what may be a little confusing and what we may decide to do is we may decide to, instead of using u over here, we will end up and we'll change it and we'll use v. So if I've already used u, then I just choose to use a different letter. So we'll do v equals x, dv equals dx, and this would be dv and dv squared. Then when you're doing the problem, you can keep your u separate from the v that's over here. All right, the antiderivative here would be negative 1/2. Then we would have u, add 1 to your power, which would put 1/2. Divide by 1/2 or multiply by 2. Okay, plus, don't do plus c, we'll put that at the end. Here we have our constant 2. Our arc, we're doing arc sine, so that would be arc sine of our u, in this case, which is v, over, v is x, over 2, and then you would do your plus c. And sometimes when this is in the really nice format, sometimes I don't even change the x to a v or to a u because it's already in the right format. So you can leave that as it is. And then we have to, one more thing, we have to put our u back in here. So we would have negative 4 minus x squared to the 1/2 plus 2 arc sine of x over 2 plus c. So there are times where you have two things and you have to split and do them as two separate problems. Like I said, be careful about using the same variable twice. If I use u here, I need to use something else over here. And usually we do u and v when we're doing this. All right, looking at example 5. 2 of these you can do and one of them you cannot do. So this is kind of the recognizing what you have. All right, taking a look at this first one. Inside here, I've got an x to the 4th. Outside here, I've got an x cubed, and I've got the square root over it. This one is going to be a power rule, and we can do that one. I am going to let my u equal 5 minus x to the 4th. My du is going to be negative 4x cubed dx. So then when I come over here to my integral, the 3 is a writer. We're going to pull that out. This I'm going to rewrite as 5 minus x to the 4th to the negative 1/2. So I'm doing power rule. Then I have my x cubed dx. I compare this to this and see if I need a corrector. I need a negative 4, so we will add that in. And then out here, we will divide by or multiply by negative 1/4 to get our corrector in. So what we are going to take our antiderivative of is negative 3/4 antiderivative u to the negative 1/2 du. And then power rule, using our power rule, we would add 1 and then multiply by 2 plus c and then finish it out. This ends up being negative 3/2 our u, which was 5 minus x to the 4th to the 1/2 plus c. So that one we can definitely do. All right, now this one, we have a couple of issues when we're looking at it. Our problem here is that if you try to let your u equal this, do you see how you're missing a power up here? And so it doesn't really do me any good. You'll be like, well, maybe I should just multiply by x over x. But the minute I do that, because this is supposed to be power rule, I end up with too much outside. So this one cannot be done. So we'll take that one out. Now let's take a look at this one and be like, well, why is this one any different? Okay, so if we take a look at this one, you may initially think that this one you can't do either. But here's what you want to look at. If I rewrite this, okay, as square root of 5 minus x squared squared, and then I have this 3x, and then we'll put the dx up here. What you notice in this one is this idea that if I let u equal the x squared, I can let a equal the square root of 5. So I'm leaning toward an inverse trig rule on this one. And then when I do my du, the du is going to be 2x dx. So really, when you're looking at this one, it does not bother me that I have this x up here. The 3 I'm going to pull out, but this x is part of the derivative of the u if I think of this as an inverse trig rule. So when we make our substitution, when we do our inverse trig rule, this is going to become the antiderivative. We'll pull the 3 out. The x dx is missing a 2, so I'm going to need a corrector. Square root of 5 minus x squared squared. I add in my corrector, so I'll do that in a different color. I put in my 2. I'm going to take out my 2. And then when we look at this, we're really doing 3/2 antiderivative du over square root of 5 squared minus u squared. And so this puts it in the form that this is an inverse trig problem. And so it would be 3/2, and then it's the square root one, so it's arc sine of the u, which is x squared, over a square root of 5 plus c. So that worked on this one. Now let's kind of go back over here and let's talk about why this doesn't work. All right, so this is not power rule because this is not the derivative of that. Okay, so not power rule. Clearly not going to be a trig rule, not going to be an exponential rule. Okay, so the only thing you have left is to try an inverse trig rule. And we'll talk about why it's not log 2 at that on this. So inverse trig rule, you might try to do the same thing, u equals x squared. But when you let u equal x squared, du equals 2x. And do you see how I have an extra x right there? So that's not going to help me. So this doesn't work either. Now, in terms of the log rule, when you're trying to do the log rule, like make the whole denominator, clearly if I made u the whole denominator, square root of 5 minus x to the 4th, that my du would be very complicated. It'd be negative 4x cubed, then 1/2 5 minus x to the 4th to the negative 1/2 dx. Do you see how this is not going to work with what we have up there either? So you kind of, as you try some of these, you'll see that they don't work. The power rule is not going to work because when I do this, I don't have the correct negative 4x cubed. I don't have an x cubed up here. So no matter what I try for this one, the u substitution does not work. And that's why sometimes you just have to try stuff and then eliminate. And once I've eliminated, not the power rule, not the trig rule, not the exponent rule, not inverse trig, and it's not log rule, you're out. That's pretty much all the things that you've got to do, so you know you can't do that one. Okay, let's take a look at example 6, and these are some ones that are where you're trying to figure out what to do and you think you can't do it, but if you do a little algebra, you're going to be able to do the problem. And so if you see something like this on the AP, and especially these are only going to be in the multiple choice section, and you're looking at it and you're like, there's no way that I can do this. How are they getting answers? One of the algebra techniques that you are going to do is to try factoring. That if you see something like this, do you see how this is a perfect square? That's really what makes this nice. If I factor that bottom, I'm going to have x plus 3 squared dx. And so by doing a little algebra on this, I can turn this into something that I can do a u substitution on. I can let my u equal x plus 3. My du would equal dx. So in terms of this problem, this is a power rule problem. My 3 doesn't have anything to do with this, so it's a writer. We'll pull that out. I'm going to rewrite this as x plus 3 to the negative 2, and then my dx. And then when I make my substitution, this is u to the negative 2 du. So it turns it into a power rule problem. So our antiderivative would be u to the negative 1 divided by negative 1 or multiplied by negative 1 plus c, or negative 3, u was x plus 3 to the negative 1 plus c. So that works out to be this problem. So factoring. So if it's one of those ones in the multiple choice and you see something like that where it's a perfect square, you try to factor it. Now, this one, when you take a look at it, you're like, if I tried factoring here, the problem is this is not a perfect square. So sometimes when you're looking at a problem, factoring this, and it does factor, we'll just kind of do up here, x squared plus 6x plus 10 is going to factor to, does it factor or doesn't even factor at all? I don't think, the discriminant. B squared is 36 minus 4 times 1 times 10, which is negative 4, so this does not factor. So you can't even use that technique. But that doesn't mean that you can't do something. When we were in Algebra 2, one thing that we did do is we did this completing the square. So let's remind yourself about completing the square. So this algebra technique is, let's try completing the square on the denominator. So what I'm going to do, and when you complete the square, this 3 will just bring it along. You group the x squared plus 6x. We're going to add something to that. We're going to take something away from that, and then we're going to add the 10. The net result here is that what you want to do is you want to add 0, but you want to end up with a perfect square right here. So we should know what the perfect square is because we just did it. Over here, x squared plus 6x plus 9 is your perfect square. But if you remember your technique from completing the square from Algebra 2, you take your middle term coefficient, the 6, you divide that by 2, and then you square it to figure out what you get to add here. And what I add, I am going to subtract because you have to balance it so that your net, you're not changing it, your net is 0. So what that does for me is it gives me 3 over x plus 3 squared, and then minus 9 plus 10 is plus 1. And then so once I do that, and I probably should add my dx in up here, then when you look at this, I have a perfect square plus 1 on the bottom. That on top can come out. This is inverse trig rule. So when I look at this, I'm going to pull the 3 out because it doesn't have anything to do with it. And the inverse trig rule that this is arc tangent of x. So I'm going to have 1 over x plus 3 squared plus 1 dx. Or let's move, because it's inverse trig, I just like to put my dx in the top when I'm doing that. So that would be my dx. And then when I go, my a is going to be 1 because of this. My u is going to be x plus 3 because that's what's being squared. My du is dx. So this becomes 3 du u squared plus 1. And so the antiderivative would be 3 times 1 over a, which is 1, arc tangent of u, which is x plus 3, over a, which is 1, and then plus c, or simplified 3 arc tangent x plus 3 plus c. So it helps us get it into a format that allows me to use the inverse trig rule. So completing the square. All right, let's take a look at C and let's see what we think we can do for C. Now you may be tempted, this one did not factor. If I work with this one, you may be tempted to think, oh, I can factor it. That's what I'm going to do. X squared plus 6x plus 8 factors to x plus 2 and x plus 4. However, this is not going to help me because you can't split, at least right now, when you have two different ones. And I can't do a u substitution because you can't let u equal x plus 2 because then nothing happens over here. So it is not going to help me to do a u substitution in terms of factoring. So I'm going to do this again. I'm going to try completing the square, and let's see what that does. Complete the square. So again, I'm going to do the same thing. Let's set it up for completing the square. Just bring the 3 with me. I'm going to have x squared plus 6x, oops, plus something, and then I'm going to subtract something outside, and then we have plus 8. All right, we want to complete the square. So I take half and square it, 9 and 9. And then we take a look at this and we rewrite it. We're going to have the antiderivative of 3. This is going to be x plus 3 squared minus 1 dx. And we don't forget our dx. Now, here's where we got into trouble in this one. And so we eliminated that we couldn't just factoring. So factoring, we'll write this up here. Factor did not work. We just tried completing the square and we get to here, but there's a problem here. You'd be tempted to be like, hey, I can do this. Actually, I think I can do this with just a u substitution. This is not inverse trig though, okay? Make sure you understand, to be inverse trig in an arctangent, you need u squared plus something squared. This is minus. But let's see what happens if I do u equals x plus 3. So we'll try a u substitution. Du is going to equal dx. So up here, in terms of substituting, I'm going to pull the 3 out as a rider. I'm going to have 1 over u minus 1, u squared minus 1, and then du. And then I go, oh, that didn't work either, because the problem is that this is still not an inverse trig, because it's not a plus. And so that didn't work. I can't do any more u substitutions. There's nothing else to do. I can't bring this up. I can't say, I have to use a different variable. I can't let v equal the entire denominator because I don't have the derivative on the top. So this is not log rule. This is not an inverse trig rule. And so with the techniques that we have right now in AB Calc, you can't do this. AB Calc students can't do. Now, when we move on to BC Calc, or you go to 201 next year, there is a technique for doing this problem. We may do this after the AP. I'm going to go ahead and just erase this because none of this strategy worked. All right, so completing the square failed. Factoring, we said failed because you can't do a u substitution with the factoring. Oh, let's go all the way back because that didn't work. So none of that worked. So the technique that you're going to use next year, so factoring initially did not work, completing the square did not work, but let's look at the factored form. 3 over x plus 2, x plus 4, and then dx. There is a technique in the second semester which is called partial fractions. And the idea of partial fractions, we're just kind of give you an overview, but we're not going to do it because it's not on our AP, is that this fraction, it must have been the sum of something over x plus 2 plus something over x plus 4 dx. That basically this is a common denominator, and that after you added these two fractions together, you ended up with 3 over the common denominator. Now, a little bit of the work to kind of show you what's going on is to get a common denominator, you would multiply this one by x plus 4, and then x plus 2 over x plus 4. This one, you would do b times x plus 2, x plus 2 over x plus 4, and then your dx. And then what you're doing is basically creating a system where you know that ax plus 4a plus bx plus 2b has to equal 3 because that's what you had right there. And so what you end up with, and another way of looking at this is to know that that's 3 plus 0x. And so ax plus bx means a plus b had to equal 0. And then the 4a plus the 2b has to equal the 3. And then you have to solve the system. I'm going to go dot, dot, dot. Because this idea is something that we actually don't need to do, but you'll learn it in Calc 2 next year. All right, let's take a look at this problem, and let's do this as some applications that we have. Okay, what I'm going to do on this problem is I'm going to first write down what exactly I'm going to do to find the area of the region. Now, it only says verify on your calculator. If I was doing this as a calculator problem, I would not do any work other than go area equals the integral from 3/2 to 9/4 of the absolute value of 1 over square root of 3x minus x squared dx. Okay. And that would be just type into my calculator and I would get my decimal approximation and I would be done. If it is not a calculator problem, then what we need to do is we are going to need to kind of sketch this and make sure that our area is always positive. Now, a little bit of knowledge here is that when you are looking at this square root is going to be a positive number because it's a principal square root. So I don't even need to do this as a calculator problem. I actually know, okay, because f of x is greater than 0, that the area is going to be 3/2 to 9/4 of 1 over the square root of 3x minus x squared dx. Okay, now we haven't talked about these definite intervals yet, but kind of coming up in our notes, we're going to talk about how we do this problem. And this is what's called the fundamental theorem of calculus, is that we are going to assume that some function capital F of x is going to be the antiderivative of this. And so if I were to take the derivative of f of x, the capital F of x, I would get this lowercase f of x, which is 1 over square root of 3x minus x squared. And so that our really the idea of this area is, remember that it calculates net change. So the first thing that we're going to do is we are going to find the antiderivative of this. And then because this is a definite integral, we are going to evaluate this by calculating our net change. This is our evaluate bar. We put our bounds on it. And the net change is to take the end y value and subtract the beginning y value on this problem. So that is going to be our strategy. So the problem that we have here, and why it's in this section, is that we need to calculate the antiderivative of this right here. So I'm going to do this work over here. So I want to do the antiderivative of 1 over the square root of 3x minus x squared. Now again, in this problem, we would be tempted to be leaning toward inverse trig because I have a number here and then I have a square there. The problem is this 3x right here. And so again, we're going to have to do a little bit of extra work on this. Would really like to have a number and then a perfect square. And so what I'm going to do is I'm going to use the complete the square strategy on that inside stuff to get it in a better form. So as we come across here, we're going to do our 1 over, bring our square root and our dx. Now the first thing I'm going to do is remember that when I complete the square, the first thing I have to do is take out the negative, because you can't complete the square unless you have a 1 in front of your coefficient. All right, so I'm going to put in something there, and now I'm going to be careful. When I put in something here, I'm actually subtracting something, so on the outside I'm going to subtract that. All right, and then I'm also, just because I think this looks weird, I'm going to move my dx and put it right here in the top so it's out of the way. All right, so I'm going to complete the square. So to complete the square, remember that you take the middle coefficient, which is -3. I'm going to divide it by 2, and then I'm going to square it, and that's going to give me 9/4. So I'm going to add 9/4 here and 9/4 here. Now that's okay because I'm actually subtracting 9/4 and adding 9/4, so my net there is 0. So I'm not changing it, but I'm putting it in a nicer form. So what that does for me is now I'm going to have dx, and then this is going to become square root of 9/4 minus, and this, the reason you do this is to make it a perfect square, x minus 3/2 squared. And I'll let you verify that that's the perfect square factoring. And so once I get it to there, I see that this is an inverse trig rule. It is going to be arc sine. And so when I do the problem, I identify my A is going to be 3/2. My U is going to be x minus 3/2. My du is going to be dx. And so when I go to do my actual answer, I'll just come down here. Notice that, do I need a corrector? No. We're doing the antiderivative of du over the square root of 3/2 squared minus u squared. So I am in the correct format to do the inverse tangent, or sorry, inverse sine. So I'm going to do my arc sine of u, which is x minus 3/2 over a, which is 3/2. And then, of course, plus c. So I have plugged this in. And then the final step is to come up here once I found this antiderivative. So all of this work down here was just work that I'm doing to find the general antiderivative. So up here, we are going to take our arc sine of x minus 3/2 over 3/2, and we are now going to evaluate this 9/4 and 3/2 and calculate our net change. So just doing a little algebra, and then kind of also dividing by 3/2 is the same as multiplying by 2/3. So this becomes 2/3 x minus 1 plus c. That might be better in terms of doing some arithmetic here on this one, because this will probably be on a no calculator. So we would have 2/3 x minus 1. So then we just plug and chug. It becomes arc sine of 2/3 times 9/4 minus 1 minus arc sine of 2/3 times 3/2 minus 1, which is going to equal, let's see what this ends up being, 9/6 minus 1. And 9/6 minus 1 is 3/6 or 1/2. So this is arc sine of 1/2 minus arc sine of 0. And then, yes, you cannot leave it there. I'm going to erase this so it's out of my way. That you can't leave it there because those are trig functions that you should be able to evaluate. The angle whose sine is 1/2 is pi over 6. Minus the angle whose sine is 0 is 0, and my answer is pi over 6. You can verify that by typing it in for the approximate. Go ahead and use your function int on your calculator to verify that this approximation and this approximation by typing in pi over 6 into your calculator is the same. All right, so let's look at a new algebra strategy. All right, another algebra strategy that we have a tendency to use. Okay, let's take a look at each of these problems. All right, so this one, you would initially look at this and be like, hey, this is going to be a trig rule. Now, one technique that we can do, okay, we could split this and do x squared over x squared plus 1, x over x squared plus 1, 1 over x squared plus 1. Now, splitting this, the 1 over x squared plus 1 would be inverse trig. The x over x squared plus 1 would be a log rule. But then the x squared over x squared plus 1 is going to, that one's kind of, that one doesn't work out so well for us. And you can't make up algebra. We can't simplify that. So the technique that we're going to use here, this new strategy, is going to be long division. That sometimes when you are looking at something like this, if the powers are the same in here and here, it's not a log rule, doesn't seem to be an inverse trig rule, and splitting it's not going to help me because this power is the same as that power. So sometimes what I decide to do is to go ahead and divide the denominator into the numerator and put it into an equivalent form, kind of like a mixed number, where you figure out what your quotient is. So just reminding you of long division, x squared goes into x squared one time. You multiply x squared plus, it'll be 0x and then plus 1. We are going to subtract. When we subtract, these two terms cancel. This term and this term cancels, and I'm left with x. This is my remainder because the degree of this is smaller than the degree of this. So I can rewrite, and this is a little review from Algebra 2. If you don't remember this, I'll let you go review long division, is that this fraction can be rewritten as the whole part, 1, plus the fractional part, your remainder, divided by x squared plus 1, and then of course your dx. Now when I split this to this, now I can do this as the antiderivative of 1 dx plus the antiderivative of x over x squared plus 1 dx. And now I have a log rule. Here I would do the antiderivative is x plus, don't put the plus c, we're going to add it on to the end. Here I would do a u equal to x squared plus 1. du would be 2x dx. I examine what I have here and I realize that I'm going to have 1 over x squared plus 1, my x dx. I examine this and I examine this and I see that I am missing a 2. So I add a 2, I add a corrector, and this becomes x plus 1/2 1 over u du, which is going to be x plus 1/2 natural log absolute value of my u, x squared plus 1 plus c. And so sometimes when the degrees are the same, we would use long division as our algebra technique. All right. Now over here, same kind of idea. You'd be tempted to let u equal the bottom, but letting u equal the bottom doesn't help me with what we have on the top. So I say, okay, if that doesn't help, and you see how this degree at the top is the one more than the bottom? So this isn't going to work into a trig rule. It's not going to work into a log rule. So I go, let's try long division on this one. So I'm going to take my x squared plus 3, and I'm going to divide that into x cubed minus 3x squared plus 4x minus 9. X squared goes into x cubed x. We multiply x cubed, and then I've got plus 3x, so it would be 0x squared, 0 at the end. We are going to subtract. These are going to cancel. Then I have negative 3x squared, 4x minus 3x plus x, and then minus 9. X squared goes into negative 3x squared minus 3. You multiply. Minus 3x squared minus 9. There would be a 0x there. We subtract. These are going to cancel. X minus 0x is x. The 9s are going to cancel. So I'm left with x. The x is your remainder. Right, so we get down till we get a remainder. I know that that is the remainder because it's a smaller degree than that. So now we're going to rewrite our integrand into the whole part plus the fraction part. The whole part is x minus 3. The fraction part would be x over x squared plus 3 dx. And then by doing that, that is going to allow me to separate. I'm going to integrate the x dx. I'm going to integrate the 3 dx. And I'm going to integrate the x over x squared plus 3 dx. So this is going to end up being equal to the antiderivative of x, 1/2 x squared. Don't put the plus c, we'll add it at the end. The antiderivative of 3 is 3x. And then over here, we have to do a u substitution. So I'll just write it up here. U would equal x squared plus 3. du equals 2x dx. This is a log rule problem. Let's put in our corrector right here. Let's rewrite it with our u substitution. 1/2 antiderivative 2x dx becomes my du, and then 1 over u. So we would have 1/2 x squared minus 3x plus 1/2 natural log absolute value x squared plus 3 plus c, and we're done with that problem. Okay, so now in this one, this new technique that we're going to do in this one has to do with the fact that you're going to use u substitution kind of in a different way. And what it is, okay, so with this u substitution, let me just show you what happens. Now, in this one, as you take a look at it, you would be like, this is not going to be a u substitution because I don't have a derivative on the outside. But this technique, you would let u equal 2x minus 1. du would equal 2 dx. And then what this substitution does, when you're kind of not, you don't have the correct derivative on the outside, you see how there's this extra x. In addition to this, what we do is we solve my u formula for x. This is like, I guess I call it, it's like a double substitution when you're doing it. It doesn't really have a name for it, but it's just one of those extra techniques that you have. If I solve for x, I would have u plus 1 equals 2x. X equals 1/2 of u plus 1/2. Okay. So what happens when I do a substitution now is this x that was the extra that is not there that I need, I'm going to take that out by substituting this in. So it becomes 1/2 u plus 1/2. The square root of 2x minus 1 is going to be u to the 1/2. And then the dx, I do need a corrector to add in because of this. So I'm going to kind of just squeeze it in right here. If I add a 2 here, I would add a 1/2 on the outside. So I bring the corrector down, and the 2 dx becomes du. Now, the reason that this is going to work and why this double substitution works is because I can't distribute the x into here because of the power and the sum, because powers don't distribute over sums. But when I rewrite it in this, do you now see how I have a sum, no power, and I have this? So the technique is that after you do this step, then you distribute. And this, remember, you add your exponents, so it would be 1/2 u to the 3/2 plus 1/2 u to the 1/2 du. So now with each of these, and then I may want to go ahead and just pull this extra constant out, make that a 1/4. Now all I'm integrating is power rule on u each time. All right, so now taking a look at it, we've managed to transform it by doing a double substitution into a problem that we can work. Now, if I don't split this into two integrals, but you just do it because it's power rule, please remember the 1/4 will distribute. The antiderivative of u to the 3/2 would be u to the add 1 5/2 2/5 plus u to the 3/2 2/3, and then that whole thing plus c. And then we simplify at the end. This would become 2. Actually, no, because I'm going to simplify. Let's undo. This would end up being 1/10. The u was 2x minus 1 to the 5/2 plus 1/4 in the 2 would become 1/6 6, and then my 2x minus 1 to the 3/2 plus c. So sometimes we have to make a double substitution. So let's check on this one. So earlier we had said that there was a problem, like I wouldn't do a u substitution initially because you're like, hey, this is not the derivative of that. But the idea here is, again, that if we are thinking of this as x squared 2x minus 1 to the negative 1/2 dx, I can't distribute the x squared into here because of the power. But if I come up here and I let u equal 2x minus 1, du equals 2 dx, and then do the same thing, solve, so x equals 1/2 u minus 1/2. If I make that double substitution, all right, we are going to need the same corrector. So if I put in a 2, correct with a 1/2, you're going to have 1/2. This x squared is going to become 1/2 u minus 1/2 squared. And then the 2x minus 1 to the negative 1/2 becomes u to the negative 1/2, and then du. And again, the only advantage of this is going to be that I can actually square this. I can't actually distribute the square root over that one, but I can distribute a square over this one, provided I FOIL correctly. The first term would be 1/4 u squared minus 1/4 times 2, which would be 1/2 u plus 1/4, because you're squaring that. And you have this times u to the negative 1/2 du. Distribute the u through. So we would have 1/4. This would be, remember you're adding your exponents, so this would be u to the 3/2 minus 1/2 u to the 1/2 plus 1/4 u to the negative 1/2. And what I've managed to do now is to turn this into a bunch of power rule problems. So we would have our antiderivative. I'm just going to put the 1/2 with each one this time. So 1/2. We would have our 1/4. The u, add 1, 5/2, 2/5, minus the 1/2 from here, the 1/2 from here, and then the rule, add 1, 3/2, 2/3, plus the 1/2 from here, your 1/4, and then your power rule, add 1, and then divide by 1/2 is multiply by 2, and then plus c. And then we just clean it up at the end. This is going to be 1/20, 2x plus, not plus, 2x minus 1 to the 5/2 minus 1/6, 2x minus 1 to the 3/2 plus 1/4, 2x minus 1 to the 1/2 plus c, and we have done that problem. All right, let's take a look at this one. Again, we have that same problem where notice that these are kind of, if I try to let u equal x plus 1, I've got an extra x up here. I could multiply this out. Okay, so there's, you know, when you get down into the weeds of integration, there may be extra things that you might try. The problem with multiplying this out, because you're like, hey, that'll give me a square on the bottom, is that it's going to be x squared plus 2x plus 1. And then when you do the derivative, you're going to get 2x plus 2. And see how I'm missing the plus 2 that I have up there? So multiplying that out is not going to work. And so that's why let's try this double substitution. If I let u equal x plus 1, du is going to be dx. And then I also see that x is going to be equal to u minus 1. So here, just doing all the substitution, I'll pull the 2 out because that doesn't appear to be worth anything. All right, now the x on top, we're going to put in u minus 1. My dx, sorry, u minus 1. The dx is du, so we can make that du, and this becomes u squared. And so now how this helps me is that this is over a single fraction now. Instead of having a sum at the bottom, it's over a single fraction. So this becomes 2. I can split my fraction, u over u squared minus 1 over u squared du, which is going to turn this problem into 1 over u minus u to the negative 2 du. So it's essentially a log rule and a power rule. So we would have 2 natural log absolute value of u, x plus 1, minus, don't forget the 2, because you got to distribute it when it's on the outside here. Your power would be u to the negative 3. No, it would not. It would be u to the negative 1, add 1, and then divide by the negative makes it a plus. And I can also go ahead and put the u back in. So I'm just saving some writing, would be x plus 1 to the negative 1, and then plus c. So that allows me to work that problem. All right, now in this one, you do want to be careful. You'd be tempted to start making a u substitution here, but it's not going to work. And what you have to recognize is that this, I actually can distribute this to this. And the reason that I can distribute this to this is because the square root, a power will distribute into a power like that, because these both have exactly the same powers. So you can think of this as dx over the square root of x minus x squared. So this turns this one, it's not even a u substitution, it turns this one into a complete the square problem. So when we look at this, I'm going to do the same thing I did on a previous one. I'm going to reorder it and factor the negative out. So it would be x squared minus x. I'm going to add something on the inside, and then this is a negative, so I have to add something on the outside to balance. And I don't have an extra constant out there, that's fine. We go ahead and we figure out what we're going to complete the square. So I have the middle term is negative 1. I divide that by 2 and I square it. So I'm going to add a fourth, which is subtracting. I'll balance with my 1/4 so that my net here is equal to 0. So I'm not changing it. And then it's going to become dx over the square root of 1/4 minus my perfect square x minus 1/2 squared. And so this turns this into an inverse trig, and it's going to be an arc sine of x. So our a is going to be 1/2. Our u is going to be x minus 1/2. Our du is going to be dx. So I do not need a corrector. So we can go straight to our arc sine. And so we would have arc sine of my u, x minus 1/2 over my a, 1/2 plus c. And we may simplify it, arc sine of 2x minus 1 plus c. And then so that would be the end of that problem. All right, let's take a look at E. All right, now this one I'm showing you because looking at this, you might try to make u equal to just the 2x. But the problem is 1 plus a square root on the bottom, you can't split it because of the plus right there. So let's try to make u, just to kind of do a couple play around with this, u equal square root of 2x, or 2x to the 1/2. So du is going to be 1/2, 2x to the negative 1/2, and then times 2, because you got to do the derivative of the inside. And so this simplifies down to, just to kind of go a little bit more, it's really the same as 1 over square root of 2x dx. And so the problem that we have here in what I've made with this u substitution is I'm missing something from the dx. Like if I kind of separate this out, I'm going to have 1 over 1 plus square root of 2x. And then I've got the dx out here. What I'm missing is 1 over the square root of 2x. You can add it in. Remember, you're only allowed to add in a form of 1. So if I add 1 over square root of 2x here, I can't add on the outside. I have to add a square root of 2x there, so that the net that I have here is I'm multiplying by 1. And then when I do that, it's kind of like a double substitution, but you have to add an extra form of 1 in there. So then when I do my substitution, this is going to be u over 1 plus u, and then all of this becomes du. And that's going to end me into the, hey, they have the same degree, and when they have the same degree, the technique was long division. So I'm just going to reorder it, u plus 1, and I'm going to divide it into u. U goes into u one time. I multiply, u plus 1. I subtract, u minus u cancels. And then this is 0 minus 1, or negative 1. Here is my remainder. So I rewrite this as a fraction. So it becomes 1 plus my fractional part, 1 over u plus 1 du. So at that point, I can now split this, and I can integrate 1 du minus, I can integrate 1 over u plus 1 du. This is a log rule. I've already used u, so I'm going to use a different variable. V equals u plus 1. dv equals du. So this is going to be the antiderivative of 1 du is going to be u minus, here I'm going to put in my 1 over v dv. So that's going to be u minus natural log absolute value of v plus c. V is u plus 1. And then I need to get rid of the u and go all the way back up here. What was u? Square root of 2x. So it'd be square root of 2x minus the natural log absolute value square root of 2x plus 1 plus c. All right, example 10 is one where they're going to give you a rule right here, and then they're going to ask you to use this rule to find this. As always, start with what you're trying to find. So I have my 1 over 3 plus 3 cosine x over 4 dx. The first thing that we should notice is that this 3 is not here. So I'm going to pull out a 1/3 from it. So it's 1 over 1 plus cosine of x over 4 dx. Now, this 1/3 is a constant. Pull it all the way out. Now here, what we're going to do is we're going to do u is equal to x over 4. du would be 1/4 dx. So I need a corrector. I'm going to add it right here, 1/4. And if I add a 1/4, I need to add a 4 out here. So let's make this 4/3 when I pulled that out. And what that allows me to do is to turn this into 1 over 1 plus cosine of u, and then that's du. Now, once I get to here, does it really matter that this is x and that's x? If this is u, no. This is a placeholder. You just use the variable that you have here. So this is going to be 4/3 tangent u over 2 plus c, and then we put our u back in, 4/3 tangent of x over 4 divided by 2 plus c, which is going to simplify to 4/3 tangent x over 8 plus c. So the idea is that you recognize that you have a rider that you're going to pull out. Then you do a u substitution, put your corrector in, and then once you get this form to match, it doesn't matter what the letter is here and here. That is the exact same form. So the only thing you have to do is to make sure that your letter matches over on that, and you can do the problem. All right, let's take a look at B. All right, this doesn't even matter that this is an integral that has an infinity in it, like the net change between what you have at the end minus what you have at the beginning. You don't have to worry about that because you don't have to actually calculate this. They're telling you that this is equal to pi squared over 12. The only difference between this and this is that 5x right there. So to calculate this, I'm going to let u equal 5x. Then my du would be 5 dx. I am going to make my substitution. Now you have to be careful here because there's going to be two places where you need a corrector. I'm going to need a corrector here because when you're looking at this, you have to get it into the form, I'll come down here, of 0 to infinity. It's going to have to be u e to the u plus 1 and then du. So if I can get this to look like this, then I can say the answer is pi squared over 12. Now, so when I'm doing this, if I'm going to put a u here, this is that double substitution, or I need to put in a corrector here for the 5. So I'm going to need a 5x here, which means I'm going to have to put a 1/5 out here. But then I also need a 5 here, which means I have to put another 1/5 here on the outside. So my corrector in this problem is actually going to be 1/25, this integral. And then the top is going to become u. This is going to become e to the u plus 1, and then that will be du. And so I can manipulate it so that these things that are here, the x, and the dx, I now have u, and du. And so provided that these are the same, I can immediately go to 1/25 and times the answer is going to be pi squared over 12. And so it doesn't matter what the variable is, it's just a placeholder. And so the net change, if I'm calling my input u, is the same net change as if I call my input x. And so this would be pi squared over whatever 25 times 12 is. Kind of not important in terms of the answer. All right, let's take a look at the next. All right, so in this one, they're giving me this definite integral. Natural log a plus b cosine x dx is equal to this value. I compare what I have here to here. Now we notice a couple of things. Do you see how this is 5x? So this is different. And then we also notice that this is pi over 5. And now this is something that we're going to talk about a little bit later, that these bounds right now, when you're looking at them, these are x's. This is an x equal to 0, and that's an x equal to pi over 5, because we are doing this with respect to x. So when I go to do a substitution on this one, okay, I'm going to let my u equal 5x. My du is going to be 5 dx. And so that when I'm looking at this, I need a corrector. Okay, I'm going to add it in red. So I'm going to put in a 5 right there. I'm going to put in a 1/5 out here. And so when I go to make my substitution for this one, you have to, it's kind of something a little new here that we're talking about, that this antiderivative is going to change to natural log a plus b cosine of u, then the 5 and the dx, okay, is going to change to du. Okay. And now remember, this is now in u, so I have to change this to be a u equals and a u equals. U is 5 times x. So if x is 0, u is going to equal 0. When u is pi over 5, 5 times pi over 5 is going to be pi. So do you see that I'm back to the same bounds that we had before? And so now when I take a look at this, you're going to be like, well, this is exactly the same thing. Here's my u and my du, and I have a pi and a 0, and I have a 0 and a pi, and I was calling it x and dx there. That does not matter when you're doing these. So the answer is going to be 1/5 of 2 pi natural log of 2. Okay, our last thing in this set of notes is just symmetry, just kind of a shortcut. And that is to kind of, when we're talking about definite integrals, that of course the integral from a to a, this is negative a to a. If you have an even function, then taking a look, if this is where your a is, and this is where your negative a is, what do we know about the area here and the area here? They are exactly the same. So notice that sometimes we don't like dealing with the negative numbers. We can switch this to being twice 0 to a, because they are the same area on the left and the right, so we can just double the positive side. So that's one shortcut. Then if the function is odd, we don't have to even do anything, because what's on the left is always opposite of what's on the right, and so this will always be 0. So they're just little shortcuts that you don't, so you don't have to do any work. So when I look at this function right here, sine is an odd function, x cubed is an odd function, and because this is odd over an even function, this is an odd function. So the minute that I am doing -3 to 3, I have to recognize that this doesn't require any work. The answer is 0, because these are all odd functions. All right, now for b, and ignore this. This is just when I imported it into here. This is -pi to pi. This is even. That's even. This one is even. So what I know is that this is the same as twice the integral from 0 to pi of 1 plus x squared plus cosine of x dx. And that is just something to do with the fact that we are going to do this. It's easier to just not deal with a negative when we're plugging in. Just a preference. It also may be a multiple choice where this is the answer that you're looking for. I'm going to leave the actual definite integral to do in another section, because I want to do definite integrals a little separately. Now here we're going from -1 to 1. We have odd, we have even, we have odd, we have even, we have odd, we have even. But because this is a sum, I can split this to be -1 to 1. I'm going to put all the odds together. Dx, and then I'm going to add to that all of the evens, -1 to 1, x to the 4th, plus x squared plus 1 dx. Now, in this problem, all of the odds, because you have symmetry over the axis, this first one's going to be 0, plus this one I can do twice the integral from 0 to 1 of x to the 4th plus x squared plus 1 dx. So it simplifies the problem into something a little easier to solve. So I just thought we would mention that, just some little shortcuts for odds. And so that will wrap up our 5.8 notes. And so you should be ready to just practice and study for the test.